Hello, welcome to our presentation on differential control systems. My name is Abhishek Ratnakumar.
I'm Sid Samadrala.
And I'm Victoria Tapman. So a differential control system is actually part of a PID controller, which stands for proportional control, integral control, and derivative control. It's used in systems where there's variables that can change, and it will move them back to a certain set defined state. So specifically looking at a derivative controller functions to sense like a rate of change within the error in the system and affects what the output of the system of the PID controller will be. Just making sure that's going to be proportional to the derivative of the error within the system. This is important because it allows for minimization of overshoot by keeping the output near the defined set state.
Here is a flow chart to help better understand the derivative control system. The derivative control system uses a set point, which is a goal that the system is set to achieve. As you can see in this flow chart, a derivative control system calculates the error between the set point and the output that's produced by the system. By comparing these two variables, the derivative control system can calculate what corrections it needs to make to reduce this error and eventually fix the error.
Two real world examples consist of cruise control in cars. So the cruise control function in a car allows it to maintain a certain speed without the use of the pedal. However, the speed of the car can change due to certain environmental factors such as the steepness of the terrain, and this can cause the car to speed up or slow down depending on the steepness. And the cruise control system would then have to use a PID control system, and this would allow the car to recognize that it's going off from the assigned speed that the user inputted, and it will adjust itself to go back to the correct speed. And the derivative action, the PID, would minimize the effect of these speed changes. The second example is temperature control, and this can be seen in the AC units. So AC units are set to certain temperatures by the user, and the system might adjusts its output through the change of the speed of the fan in order to achieve the desired temperature that was set by the user. Throughout time, though, the temperature in the building or outside can change, and this would mean that the AC unit would have to use a differential control system to recognize these changes and adjust its temperature output to reach its assigned and original temperature value. So some of the pros and cons of this system is that it consists of the pros of manual changes aren't needed to correct the system. It also minimizes overshoot by counteracting P&I and allows for more precise changes and decreases time to reach set point and also decreases the amplitude of oscillations. Some of the cons consist of the derivative controllers do not exist by themselves, must be part of a PID controller, and also that the derivative control is not needed in most cases. Most systems only require a PI control.
And in terms of effectiveness of using a derivative control or adding it to a PI system, making it a PID system, would be very effective for our robots that we use. Because our robots are small masses and they could go through changes within the servos and the differences. By using a PID controller rather than just a PI controller, you have an added level of precision. And so the robot's less likely to make a quick change and veer off course. So it's going to stay closer to the line, which allows for it to follow the line at a more effective rate.
Here are our references, and thank you for watching our presentation.